Hey everyone, welcome to Simplilearn. Today we will be learning about computer networking basics. If you have ever wondered how your messages reach your friends just in seconds or how a YouTube video streams flawlessly across the world, that's the magic of networking. In this tutorial, we will decode what networking really is, how it works, and why it's the backbone of our connected world. That said, if these are the type of videos you'd like to watch, then hit that like and subscribe buttons along with the bell to get notified whenever we host. Before we begin, if you are interested in growing your career in cybersecurity, then an executive certification is a great way to start. The Advanced Executive Program in Cybersecurity by Simplilearn is the right choice for you. This is a 6 months live and interactive online program from IIIT Bangalore, CompTIA, and Microsoft as authorized training partners. This program helps you master key in-demand skills like Metasploit, Nmap, and many more. This program adds great executive certifications from IIIT Bangalore and Microsoft. You'll also get career support including resume help, mock interviews, and job assistance. In just 6 months, you will master ethical hacking, penetration testing, ransomware analysis, security architecture, along with 16 plus other skills. Whether you're switching careers or upskilling, this course on Advanced Executive Program in Cybersecurity gives you practical expertise to stay ahead. Hurry up and enroll now. Find the course link in the description box below and in the pinned comments. Now, without further delay, let's get started with a small quiz. Which protocol is used to convert domain names into IP addresses? Your options are A. HTTP, B. DNS, C. DHCP, and D. FTP. Do let us know your answers in the comment section below. Now, without further delay, let's get started. So, let's start with Module 1. So, the Module 1 will give you a brief introduction to computer networking. So, welcome to our Module 1 of our computer networking tutorial. Before we dive deep into protocols, devices, and architectures, let's start with the most important question. What exactly is networking, and why does it matter so much in our digital lives today? Think of today's lesson as understanding the heartbeat of the digital world, the invisible connections that make communications possible. Now, what is networking? At its core, networking is the science of connecting multiple entities so they can exchange information. So, in human terms, imagine a community where everyone wants to share messages. You pass a note to your neighbor, they pass it to theirs, and the message moves through the chain. Computers operate in a similar way. Networking allows them to communicate with each other, share files and media, access applications, and of course, connect to the internet. Every click, every video stream, and every online transaction depends on the network systems talking to each other seamlessly. Now, what makes up a computer network? When we say computer network, we are referring to a collection of devices working together, such as laptops, smartphones, smart TVs, cameras, printers, IoT devices like smart lights or thermostats, etc. These devices are linked through wired connections like Ethernet cables, wireless links like Wi-Fi or Bluetooth, or etc. To make all these communication reliable, we depend on hardware components such as routers to direct traffic, switches for connecting multiple devices with a network, modems translating signals between your home and ISP. And underlying everything are network protocols, formal rules that define how data travels, how devices introduce themselves, and how information flows without collisions or errors. Next is the IP addresses, the digital identity system. Now, imagine trying to deliver a package in a city with no house numbers. You should be lost instantly. Networking solves this using IP addresses, unique identifiers that every device receives. These addresses can be assigned by the Internet Service Provider or ISP or by your home router when you're inside a local network. Now, think of IP addresses as the digital equivalent of a postal address. Without them, data wouldn't know where to go. Now, let's go through a simple example. Your home network. Now, let's go to a detailed storytelling. Let's break everything down with a simple example. Picture a typical home. You have a laptop, a phone, and a smart TV, maybe a printer as well, and a couple of other IoT devices. Here's how everything gets connected. All your devices join the home network through your Wi-Fi router. The router acts like the manager of small digital neighborhood. The router connects to your internet service provider, your local internet provider. So your ISP connects to larger national ISP networks. Those national carriers connect to international backbone networks. Finally, this global mesh leads to your website and servers anywhere in the world. So when you open YouTube or try to download a file, your request travels through several layers of network. And it also passes through multiple routers and submarine cables and finally reaches the server hosting that particular content piece and then returns the data that you asked for. All this happens just within milliseconds, faster than you can blink. Now, let's look at the big picture. What is the internet? When we zoom out from your home network, the internet becomes easier to understand. The internet is a massive network of networks. It connects millions of ISPs, internet exchange points, data centers, cloud platforms, and countless private and public networks. These connections span the globe via high speed optical fiber cables laid across countries and even under the oceans. Every message you send, whether a WhatsApp text or a bank transaction, travels through this giant mesh of interconnected systems. Now, let's understand why this matters the most. Before we go deep, understanding this foundation is very crucial. Everything we cover in the upcoming next modules, protocols, routing, switching, OSI layers, firewalls are built on this simple idea. Now, networking is the art and science of connecting devices, so information can move reliably from one point to the other. If this base is clear, the rest of the networking becomes much easier to understand and analyze. This wraps up the module 1. In the next module, we will break down the core building blocks of networking, including network types, transmission, media, and key terminologies every professional should know. Now, the module 2 will be all about how internet requests work. What happens when you type google.com or simplilearn.com? Have you ever wondered what really happens when you open your browser and type a website address like google.com? It feels instant, almost magical, but behind that single action is a highly coordinated chain of events happening across routers, ISPs, data centers, and even undersea cables. In this module, we are going to unpack that entire journey step by step, so you understand exactly how a simple web request travels across the world and comes back to you in just milliseconds. So let's start with step 1. Your device creates a request. The moment you press enter or click, your device packages your intention into a structured message. This message is essentially saying, I need Google's homepage. Your device wraps this request in layers of technical information like your IP address, the destination server, and the protocol being used. This is the starting point of your data's journey. Now, let's dive into step 2. Step 2. It decides the next hop where the request must go to continue its journey. Think of the router as a smart traffic controller that decides the best path for your data to reach outside world. Now, let's dive into step 3. The router forwards your message or request to your ISP or your internet service provider. After identifying that the destination is outside your home network, the router forwards the request to your internet service provider, typically your city level or regional level providers. Your ISP functions like the highway system for your data. It has higher infrastructure, higher bandwidth, and multiple connections to broader networks. Now, let's dive into the step 4. The ISP sends it to national backbone networks. From your internet service provider, the request escalates into a bigger network known as the national backbone. These backbone networks are built using high-capacity fiber optic lines, major switching centers, internet exchange points, and much more. At this level, data moves through extremely fast, redundant, and optimized pathways designed to handle massive amounts of traffic. If Google servers are within your country, the request might only travel through these domestic backbone routes. But if the content is hosted abroad, the journey continues. Now, let's go through that in the step 5. International submarine fiber cables. If the nearest Google server is outside your country, your request travels through undersea fiber optic cables, the global highways of the internet. These cables stretch across oceans connecting continents through thin strands of glass that transmit data at near light speeds. This global infrastructure ensures that your data can reach any server in the world regardless of the geographic. Now comes the step 6, reaching Google's nearest data center. Your request eventually arrives at Google's closest data center. Google has strategically placed dozens of these centers globally to reduce latency and speed up response time. Inside the data center, massive server clusters, load balancers, distributed storage systems, and much more. All these work together to process your request efficiently. Now, how Google responds to your request is our next step. Once your request reaches the server, Google performs three main actions. First one, it validates your request. The server checks who is requesting, is the request safe, what page or resource is being asked for. These are the three confirmations that it will perform. Next, it generates a response. Google prepares an HTML document, which is simply the structured code of the web page, not the actual visual rendering you see. The server does not send any fully drawn web page. It only sends the blueprint. Third stage is sending the code back to you. This HTML response begins its journey through international cables backbone networks, your ISP, your home router, and finally reaches to your device. Now you need to wonder what your browser does with it. With the response, now your browser takes over. It performs a series of steps to convert raw code into a beautiful interactive web page. First one, it interprets the HTML. This is like reading the skeleton structure of the web page. Second, it fetches additional resources. Your browser then asks for more items like CSS for styling, JavaScript for interactivity, images and icons, fonts, and other animations. Each of these is a separate request made to the server, sometimes dozens of them within milliseconds. Now, the third part, rendering the page visually. Finally, the browser paints everything on your screen: layout, colors, buttons, search logo, etc. This is the moment you see Google's homepage fully loaded on your screen. Now comes the most impressive part, the entire round trip from typing google.com to seeing the page appear. The whole process typically completes under just 200 milliseconds. That's 1/5 of a second. This speed is possible because of highly optimized routers, fast DNS systems, distributed global data centers, massive fiber networks, efficient browser engines, and a lot more. All of these working together in perfect coordination. So, next time you hit enter or click on your browser, just remember your request has traveled across cities, networks, or even sometimes oceans and data centers and came back almost instantly. In the upcoming module, we will explore how devices talk to each other, how data travels in packets, and what ensures that nothing gets lost along the way. And that brings us to the module 3, which is on networking devices and communication essentials. So far, we've explored what networking is and how an internet request travels across the globe. But networking is more than just computers talking to each other. In this module, we will explore the diverse devices that make up networks and the essential rules that allow them to communicate efficiently. So, the first one, beyond computers, other network devices. When we think of networking, most people imagine just laptops or desktops. But in today's networks are much more diverse. Devices like printers, IP cameras, smart bulbs, home assistants like Alexa or Google Home, IoT sensors in smart homes or factories all participate in network communication. Now, to understand them better, let's go through a simple example. A smart bulb receives commands from your phone to turn on or change color. A printer receives a document from your laptop over Wi-Fi. A security camera streams video to your phone or cloud storage. Each of these devices is both a sender and a receiver of information contributing to a complex web of data flows. Now, let's discuss the communication rules that are required. Protocols for all these devices work together without chaos. They follow protocols, which are predefined set of rules that govern how devices talk. Protocols define how communication starts, who sends data first and how devices initiate a connection, how data travels, the path it takes, the format, and the timing. Now, error handling is the next one. What happens if data gets lost, corrupted, or delayed? Followed by error handling, we have interpretation at the receiver's end, which is about ensuring the data is understood correctly. Think of protocols as traffic laws for data. Without them, devices would be sending packets blindly, causing collisions, confusions, and errors. Now, why protocols matter in daily life? Protocols enable smooth sharing of resources. For example, sending a Word document to a network printer, accessing shared storage in your office network, streaming live video from a security camera to a phone app. Even your smart fridge relies on protocols to check the software updates or communicate with your smartphone. Without protocols, the data from your smart bulb could end up on your printer, or your security camera feed might never reach your phone, or a lot more worse. Now, let's discuss the devices and roles in a network. It's helpful to understand two broad roles of devices in a network. The first one, end devices, or in other terms, clients. These are the devices that initiate or consume communication, like computers, smartphones, smart TVs, IoT sensors, and a lot more. They request data, process it, and often generate new data. Next comes the intermediary devices, or also known as the network infrastructure. These devices help move data from one place to another, like routers determine the best path for data. Switches connect multiple devices within a network. Access points enable wireless devices to join the network. Now, both types of devices work together seamlessly thanks to the networking protocols. So, to understand this better, let's go through an example. Sending a document to a printer. Let's put it all together with a simple use case. You hit print on your laptop. The document is broken into data packets following a protocol like TCP/IP. The laptop sends these packets to the switch, which is then forwarded to the printer. The printer reassembles the packets and prints the document. Any errors, like lost packets, are corrected automatically by the protocol rules. This entire process might take just mere seconds, but it illustrates how multiple devices and protocols work in a synchronized way. Next, we have real-world networking impact. Networking isn't just a technical setup, it's the foundation for modern, smart living. IoT devices in smart homes or factories depend on consistent communication. Offices and enterprises rely on seamless device communication to ensure productivity. Even emergency systems, traffic lights, and healthcare sensors rely on robust network protocols. Understanding how devices communicate and the rules they follow is essential for anyone learning networking. To sum up, networking extends beyond computers to include printers, cameras, smart devices, and IoT sensors. All these devices follow protocols that ensure data is transmitted, interpreted, and error checked correctly. In the next module, we will dive deeper into network types, topologies, and how devices are organized for optimal communication. Now we enter module 4, which is about network topologies that explains us how devices are arranged and connected. So, have you ever wondered why some networks perform smoothly while others slow down when more devices join? The secret often lies in something called network topology, which is the blueprint that defines how devices are arranged, so how they connect and how data flows between them. In this module, we will break down the classical topologies that form the foundation of modern network design. So let's start with the first question. What is network topology? A topology describes how devices are arranged and interconnected inside the network. It answers basic but critical questions like where are devices placed, how are they physically connected, how data travels from one device to another, and a lot more. Understanding topologies helps engineer design networks that are faster, more reliable, and easy to maintain. Now, let's start with the types of topologies. First, we have the bus topology. Imagine a single main road running through a town, and every house opens directly into this road. That's the bus topology. How it works? All the devices connect to one central cable known as the bus or backbone. When the device sends data, it gets broadcast into every device on the line. Only the intended receiver reads the message and the others ignore it. Advantages? Simple to set up, low cost, and minimal cabling. And now let's also discuss the limitations. If the cable breaks, the entire network fails. Performance may decrease if more devices join. Not used widely today, except in very small or legacy setup. Bus topology is important historically because many early LANs were built on this way. Now comes the second type of topology, which is the ring topology. Picture a circular track where messages run through each station in a loop. That's the ring topology. How it works? All devices form a closed loop. Data travels in one direction, passing through each device. Each device acts like a relay, forwarding the data to the next one. Now let's discuss the advantages. Predictable performance, suitable for every distributed traffic. Now, every topology comes also with its limitations, so let's discuss them. A failure in one device or cable can bring down the entire loop. Delays increase as more devices join. Modern networks avoid single rings and prefer dual ring designs for redundancy. Ring networks were popular in older enterprise systems like token ring. Now comes the third type, which is star topology. This is the most common topology in the modern networks, especially for home, Wi-Fi, office, and office LANs. Now let's discuss how it works. All devices connect to a central hub or switch. The switch acts as the traffic controller. It directs packets to the correct device using the MAC addresses. Now let's go through the advantages. It's easy to expand and troubleshoot. Failure of one device doesn't affect the others. Excellent performance due to dedicated links to the switch. Now let's also discuss the limitations. If the central switch fails, the entire network goes down. It needs more cabling than bus or the ring topologies. Most Ethernet cables or LANs today use the star topology because it balances reliability and performance. Now, let's move to the fourth type of topology, which is the mesh topology. Imagine every device having a direct route to every other device. No detours, no intermediaries. That's the mesh topology. Now, let us also understand how it works. Each device connects directly to every other device. Data can take multiple paths to reach the destination. Extremely resilient and reliable. Now, let's also discuss some advantages. It has high redundancy, excellent reliability, no single point failure. It's ideal for mission critical environments. Now, it's not like it doesn't have limitations. It also has limitations and some disadvantages. Let's go through them. It's very expensive due to massive cabling. It's complex to manage and configure. Mesh is used in environments requiring zero downtime, like military networks, stock exchanges, and data centers. Now, apart from these topologies, we have another one which is called as hybrid topology. Real world networks rarely use a single topology. Instead, they combine them. Star bus, bus ring, mesh stub. For example, instead, they try to combine them like star with bus with ring, mesh with star, and a lot more other combinations. For example, a large office may use star topology on each floor, but floors might connect through a bus or mesh backbone. Hybrid designs offer the best of multiple worlds, balancing cost, reliability, and performance. Now, wireless and ad hoc topologies are our next topic of discussion. With wireless networks, the concept of topology expands beyond cables. Wi-Fi networks typically use a star-like approach. A router acts as a central node. Devices like phones and laptops connect to it wirelessly. Next is hotspots. It's a temporary access point. It allows quick, on-demand network formation in public areas. Next is ad hoc networks. Devices connect directly to each other without routers. It is perfect for temporary or device-to-device communications. It is also used in file sharing, emergency networks, and IoT experiments. Wireless topologies provide flexibility compared to traditional wired structures. So, summing it up, network topologies form the architectural foundation of all communication systems. Understanding them helps you design networks that are efficient, secure, and highly reliable. In the next module, we will explore network types, which are LAN, WAN, PAN, and MAN, and understand where each of these fits in real world scenarios. And that brings us to the module 5, IP addressing and MAC addressing, the identity system of networks. So, imagine a world where every device, your phone, your laptop, smartwatch, printer, or even your smart fridge, needs a unique identity to communicate. Just like humans use names and IDs, computers use IP addresses and MAC addresses to identify themselves on a network. In this module, we are going to break down exactly how these addressing systems work and why they're essential for modern communication. So, part 1. What is an IP address? An IP address is a unique identifier assigned to every device connected to a network. Think of it as a postal address of a device. Without it, data wouldn't know where to go. These are two major versions of IP addressing used today. First one is IPv4, the original addressing system key characteristics, 32-bit address format like 192.168.1.1. Roughly 4 billion in total addresses. This seemed more than enough back in 1980s. But with today's explosion of smartphones, cloud servers, smart TVs, IoT systems, wearables, the available IPv4 space is almost completely exhausted. Now let us also know why IPv4 ran out. Every connected device requires an address. By the early 2010s, billions of devices were coming online. The IPv4 simply couldn't scale that level. Now comes the IPv6 into the picture. So IPv6, the future-proof addressing system. To overcome IPv4 limitations, we transition to IPv4. Key characteristics: 128-bit address format. For example, 2001 DB8 85A3 8A2 370 7334. So it might be a little complex. I'll leave that in the screen so that you have a quick reference. So this supports trillions, up to trillions of unique addresses. This is designed for future where everything from cars to light bulbs needs internet connectivity. So why IPv6 matters? So it ensures infinite scalability, better routing efficiency, improved security features, smooth functioning of IoT ecosystems, and a lot more. IPv6 is gradually replacing IPv4. Though both coexist today using a technique called dual stack networking, it is a little complex. Now, let's discuss IP address classes. Now, let's go with IPv4 only. So, before IPv6, IPv4 networks use classes to allocate address ranges. Class A for large network, millions of hosts used by big enterprises or ISPs. Class B for medium-sized networks, universities, corporations, government offices, and a lot more like that. Class C for small networks, most home and office networks fall here. Limited number of devices per network. Next is Class D, which is used for multicasting, streaming, conferencing, IPTV. Next is our Class E, which is reserved for research and development. Though class-based addressing is less common today due to CIDR, which is classless interdomain routing, understanding the classes helps build foundational IP knowledge. Now, let's discuss about static versus dynamic IP addresses. First comes the static IP. It is permanently assigned. It does not change. It is used for web servers, application servers, email servers. It ensures stable, predictable connectivity. Next comes the dynamic IP. It is mainly assigned temporarily by DHCP. So DHCP stands for Dynamic Host Configuration Protocol. It is common for home devices, mobile devices, guest networks. It is cheaper, easy to manage, and automatically rotates. Most residential users give dynamic IPs from ISPs, while businesses often pay extra for static addresses. Now comes the part 2, which deals with MAC addressing, the hardware identity system. While IP addresses identify devices globally, a MAC address identifies the device locally within a network. What is a MAC address, you ask? It is a unique hardware identifier assigned to every network interface card, or NIC for short. The sample format is on the screen. You can see that it's coded as 00:1A:7V:00:47. It is actually built into the device by the manufacturer, managed globally by the IEEE. Why MAC addresses matter is our next question. MAC addresses are used by switches to forward data inside a local area network, routers to authenticate devices, operating systems to manage network interfaces. Your device's MAC address typically never changes unless you spoof it manually. Now, let's discuss about MAC filtering for small network security. Many routers offer MAC filtering, which only allows devices with approved MAC addresses to join the network. Now, let's go through the benefits. It prevents unauthorized access, useful for home networks. It adds a simple layer of security. However, it's not completely foolproof. MAC addresses can be spoofed, but it's still an effective measure for basic control and device whitelisting. Now, let's discuss the differences between IP address and MAC address. So, IP address versus MAC address is our next topic. The quick comparison. Here's a quick comparison table right on my screen. We can compare an IP address to a MAC address. The distinction lies in their identity and scope. An IP address identifies a device on a network and is assigned dynamically by the ISP router or DHP server. It can change over time and it's used for communication across different networks, including Internet routing. IP addresses follow either IPv4 or IPv6 formats. A MAC address, on the other hand, identifies the physical network interface of a device. It's assigned at time of manufacturing, making it mostly permanent. MAC addresses operate within the boundaries of local area network and follow a fixed 48-bit hexadecimal structure. Together, these two identifiers work like a successful learner and a reliable product, each with a distinct role but both essential for maintaining credibility and seamless communication across the networks. Together, IP addresses and MAC addresses form a dual identification system that ensures data reaches the right device both globally and locally. To summarize, IP addressing gives devices a global identity, while MAC addressing gives them a local hardware identity. Both systems work together to make modern networking scalable, organized, and secure. In the next module, we will explore subnetting and how networks are efficiently divided, a crucial skill for both network engineers and system administrators. So that brings us to module 6, MAC addressing, the hardware identity of every device. If IP addresses tell the data where to go, then MAC addresses tell it who exactly it belongs to once it reaches the local area network. Think of the MAC address as the serial number of your network identity, unique, permanent, and globally recognized. In this module, we will decode MAC addressing, why every device has one, and how it plays a crucial role in local communication. So let's start with what is a MAC address. A MAC address or Media Access Control Address is a permanent hardware identifier assigned to every network interface card or NIC for short. This means your laptop's Wi-Fi card has a MAC address, your Ethernet port has a MAC address, your phone, your tablet, your smart TV, printer all have their own MAC addresses. Example format. A typical MAC address looks like this. You can see it on my screen. 00:1A:C:7B:00:47. So basically, it contains 48 bits represented in 12 hexadecimal digits, usually grouped in pairs separated by colons. Now let's dive into the key characteristics of MAC addresses. First one, it's burnt into hardware. MAC addresses always are literally etched into the network interface during manufacturing. This makes them stable and consistent. Even if you reinstall your operating system or change your network settings, they will not be changed. Second, it is managed globally by IEEE. The first half of a MAC address identifies the manufacturer. Companies like Intel, Realtek, Broadcom, Apple all have their own assigned ranges. This global standardization prevents two devices from accidentally sharing the same identity. Third, it is used for local area communication. While IP addresses route packets across the internet, MAC addresses operate on the local network. This is where switches come into play. Switches maintain MAC tables. These tables map MAC addresses to specific ports. When data arrives, the switch forwards it directly to the correct device. This leads to faster, targeted, and collision-free communication inside a network. Now, with this, let's move to the next question. Why MAC addresses matter in networking? So, MAC addresses ensure accurate device-to-device delivery, efficient switching inside LANs, unique identification at the hardware level, secure, and traceable traffic flow. Without MAC addressing, every device would rely solely on IP addresses, which are too dynamic and too external to handle local traffic efficiently. Now let's also discuss a bonus concept, MAC filtering. Some routers provide a security feature called MAC filtering. How it works is your next question. You can specify exactly which devices are allowed to connect to your network by listing their MAC addresses. The router checks the address of every connecting device, compares it against the allowed whitelist, and grants or denies the access based on the whitelist. So now, where MAC filtering helps us. Home Wi-Fi, small office networks, IoT-heavy environments, guest networks, it adds an extra layer of control by ensuring that only approved devices can join the network. A small caution though, while MAC filtering is useful, it is not foolproof. We should remember this. MAC addresses can technically be spoofed, but for small environments, it's still a practical and effective access control tool. Now, the next question will be about a quick comparison. Now we have a quick comparison of MAC versus the IP addresses. A quick recap. Here's a quick info from the table on my screen. A MAC address serves as a hardware identifier. It's burned into the network interface card by the manufacturer and remains permanent throughout the device's life. It's primarily used for communications within the local network, and it operates at the data link layer or layer 2 of the OSI model. In contrast, an IP address functions as a logical or network level identifier. It's assigned dynamically by an ISP or a router or a DHP server, and it can change over time. IP addresses enable communication across networks, making them essential for internet routing. They operate at the network layer, which is layer 3 of the OSI model. Together, MAC and the IP addressing creates a dual layer identity system that ensures data reaches the right device in the right network segment. Now, with this to summarize, MAC addresses may seem technical, but they are foundational to how devices communicate inside local networks. By understanding them, you gain a deeper insight on how switches operate, how network access is controlled, and how data flows efficiently. In the next module, we will move into subnetting, the logic behind dividing networks smartly for security, scalability, and better performance. Now, next comes the module 7, which is about transmission modes. So, data transfer between devices follows specific communication modes that define direction, flow efficiency, and use case suitability. These modes directly influence network throughput, latency behavior, and the overall interaction pattern between the devices. Now, let's start with the first mode, the simplex mode, a one-directional data flow where information moves strictly from sender to the receiver. Let's also go through the key characteristics. Receiver cannot respond back, low complexity, low cost, used in systems where feedback is unnecessary. And let's also go through some examples. For example, keyboard to computer input stream, broadcast TV signals, and similar ones. Now, why it matters? Simplex is ideal where reliability comes from controlled, predictable output rather than back and forth communication. Now, let's dive into the next one. Half duplex mode. Communications flow in both directions, but not at the same time. So, let's go through the key characteristics to understand it. Devices take turns to send the data. It reduces collision risks but increases delay during high traffic. It's suitable for shared communication channels. Now, let's also go through some examples. Walkie-talkies, legacy Ethernet using CSMA or CD. And now let's also understand why it matters. Half duplex is efficient in environments where full two-way communication exists, but simultaneous transmissions isn't critical. Now, the third type is full duplex mode. Both devices send and receive data simultaneously, offering maximum efficiency. Let's also go through some key characteristics. Doubles potential data throughput, no waiting for turn taking, standard in modern networking hardware. So some of the examples are telephone, modern Ethernet switches, Wi-Fi 6 with MU-MIMO, and OFDMA improvements. Now, why it matters? Full duplex is foundational to modern high-speed networks where concurrent data exchange is essential for performance like video calls, cloud syncing, and real-time apps. Now, let's go to the next module. So the module 8 is about networking devices. Modern networks rely on specialized devices that manage data flow, maintain traffic efficiency, and ensure secured connectivity. Each device plays a distinct role in how information moves across local and global networks. So, the first one, hub, a basic legacy networking device that operates in or at the physical layer. To the first layer and its characteristics. So, let's discuss the characteristics of the first layer. It broadcasts incoming data to all ports regardless of the destination. It cannot read MAC addresses, so no filtering or intelligence. It causes unnecessary traffic and collisions in large networks, mostly replaced by switches due to inefficiency. So, what's the use today? It is rarely used, primarily in small labs or troubleshooting scenarios. Now comes the second layer, which is called as a switch. It's a device that forms the core modern LAN communication. So, what are its characteristics? It maintains a MAC address table to identify connected devices, directs data only to the specific destination port, reducing collisions. It supports full duplex, enabling simultaneous send or receive, scales efficiently for enterprise networks. Now, what's the role? It's the backbone of nearly all wired LANs due to speed, intelligence, and security features. Next comes the router, a layer 3 device which is responsible for inter-network communication. Let's also discuss the characteristics. It connects different networks, for example, home LAN, internet, uses IP addressing, routing tables, and protocols. OSPF, BGP to choose best paths, enables NAT, firewalling, DHCP, and packet filtering. It's critical for both home and enterprise networks. Now, let's also go through the roles. Essential device enabling global connectivity and secured optimized routing. Fourth one is the gateway. It's a specialized router that acts as the entry and exit point between a local network and external networks. Now, let's also go through the characteristics of a gateway. It translates traffic between different network architectures or protocols. It handles network boundary functions such as authentication, inspection, and policy control. Default gateway in homes equal to your Wi-Fi routers, IP, example 192.168.1.1. Let's also go through the roles. Gateway ensures communication beyond the local network, especially the internet. Now, let's proceed to our ninth module. So the ninth module is all about network classifications, which are LAN, MAN, WAN, WAN, and SAN, SAN. When we talk about computer networks, one of the most important ways to understand them is by looking at how large they are built and what purposes they serve. Every organization, from a startup to a global tech giant, relies on a different kind of networks based on their scale and performance needs. In this module, we will break down 4 major network classifications. First one is LAN, next MAN, third is WAN, and lastly SAN, SAN. Each one forms a different layer of our digital world. First one, LAN or local area network. Let's start with the most familiar one, the LAN or local area network. A LAN covers a small localized area, typically your home, a small office, a school building, a college campus, and within this space, devices can communicate through high-speed, low-latency links, often using Ethernet cables or Wi-Fi. Think about your home network for a moment. You have a router, maybe a couple of laptops, some mobile phones, a smart TV, and perhaps a printer. All of these devices form a LAN. Now, why LANs matter? They are designed for speed and efficiency. You can transfer files quickly, stream videos without delay, and access shared resources like printers or storage device with almost no lag. In other words, a LAN is like a tight-knit community where everyone is close together and communication is almost instant. And the next one is MAN or MAN or Metropolitan Area Network. Next, we scale up to MAN or Metropolitan Area Network. A MAN connects multiple LANs across an entire city or a metropolitan region. This is the type of network used by telecom companies, broadband providers, citywide government networks. If a LAN is a neighborhood, then a MAN is an entire city. Telecom providers use MANs to distribute internet access to millions of homes. Your home router may connect to a fiber line running down your street, but that LAN actually sits inside a much larger MAN operated by your ISP or internet service provider. Key idea: MANs are about city-level connectivity carrying high-speed data across kilometers of fiber infrastructure. Now comes the third type, the WAN. Now, let's move into the giant WAN or wide area network. WANs cover extremely large geographical areas, national-wide, cross-continent, or even globally. The best example of a WAN is the internet itself, a massive network of interconnected ISPs, data centers, and global backbones. Your request to visit Google might start inside your home's LAN, but it travels through your ISP's MAN and eventually be routed across WAN links that span countries and oceans. WANs rely on submarine fiber cables, satellite links, long distance fiber backbones, or even Internet Exchange Points or IXPs for short. Now, why WANs matter? They make global communications possible, from international payments to video calls to cloud services and a lot more. So, if a LAN is your neighborhood and MAN is your city, a WAN is a world's largest digital highway system. With that, we go to SAN, which is Storage Area Network. So, finally, we have SAN or Storage Area Network. A SAN is not defined by the geographical size, but it's defined by the purpose. And SANs are high speed specialized networks designed specifically for large scale storage, data center operations, cloud provider infrastructure. Whenever a cloud platform like AWS or Azure needs to read or write petabytes of data at lightning speeds, the action happens inside a SAN. SANs typically use fiber channel connections, high performance switches, redundant storage arrays, and a lot more. These networks guarantee low latency, high throughput, and zero communication downtime, making them backbone of enterprise storage. Think of SANs as the expressway lanes inside a data center, ensuring the storage layer performs flawlessly even under massive workloads. Bringing it up all together, a simple way to visualize the classifications: LAN, your home or office network; MAN, your entire city; WAN, your entire country or the whole world; SAN, the high-speed storage engine inside a data center. Each classification serves a unique purpose, and together they form the layered architecture of modern communication, from a small household to the global internet to hyperscale cloud platforms. Now, let's proceed with the 10th module. So the 10th module is about OSI model and TCP IP model. In this module, we are diving into one of the most important topics in networking: the OSI model and the TCP IP model. These two models act like blueprints that explain how data travels from one device to another. Whether you are sending an email, printing a document, or streaming a YouTube video, think of them as layered frameworks. Each layer performs a specific job, and together they create smooth communication experience from your device to the destination. Let's start with the OSI model. The OSI model stands for Open Systems Interconnection and breaks down network communication into 7 structured layers. You can think of these layers like steps in a communication pipeline. Each one adds something new to the data before passing it on. Let's explore them one by one, starting with the physical layer. This is the foundation. It handles the actual transmission of electrical or optical signals. The key responsibilities: cables, connectors, optical fiber cables, voltage levels, bit rates, physical network interfaces. If data transmission were a road, the physical layer would be the asphalt and traffic lanes. Second one is the data link layer. Here, the raw bits become structured frames. The key responsibilities are MAC addressing, error detection, switch-to-switch communication, and a lot more. This layer ensures that data travels safely between two devices directly connected on the same network. Think of it as a well-organized envelope that wraps your information safely. Next comes the third layer, which is also known as the network layer. This is where addressing and routing come into the play through the IP protocol. The key responsibilities are IP addressing, routing decisions, packet forwarding across the network, and routers operate specifically in this area. This layer answers the question: which path should the data take to reach its destination? After this, we have the fourth layer, also known as the transport layer. This layer ensures reliable delivery. Now let's discuss the key responsibilities. These are the TCP and UDP, error recovery, and end-to-end communication. TCP checks if every packet arrives safely. UDP just sends the data quickly without guarantee. This is like choosing between a secure courier, which is TCP, and an express delivery, which is UDP. Next comes the fifth layer, or the session layer. This layer controls the start management and end of the communication sessions. The key responsibilities are opening sessions, maintaining sessions, and closing the sessions. Think of it as the meeting host who keeps track of who is speaking and when the meeting ends. Next, after this, we have the sixth layer, also known as the presentation layer. This is the translator layer. The key responsibilities are encryption, decryption, data format conversion, and compression. This layer ensures data is in format the receiving system can understand, just like translating one language into another. And lastly, we have the application layer. The application layer is the closest end to the users. The key responsibilities of application layer are web browsing, which is the HTTP, email, SMTP, file transfers, FTP, and remote login, which is SSH. This is where applications interact with the network to deliver the experience you see on your screen. Now, with the OSI model discussed, let's switch to TCP/IP model. It's a practical 4-layer framework. Now let's compare this to the TCP/IP model, which is more compact and directly used on the internet. While the OSI model is theoretical, the TCP/IP model is practical. It powers your real-world communication every day. It consists of 4 different layers. This layer combines the functions of OSI physical plus data link layers. Now let's also go through the responsibilities of this particular layer. It ensures physical connections, MAC addressing, frame transmission, and a lot more. It's your local network environment. Now let's discuss about the second layer, which is the Ethernet layer, which is equivalent to OSI network layer. Let's discuss the responsibilities. It is to deal with IP addressing, routing, packet forwarding. This is where decisions like which router should this packet take next happens. Now, we will deal with the third layer, which is called as the transport layer. It matches the OSI transport layer, and the following are its responsibilities. TCP UDP communication, reliable or fast delivery, managing data segments. This layer ensures your packets arrive in the right order at the right place. Now is the last layer, which is the application layer. This particular layer combines the OSI model's application, presentation, and session layers together. Responsibilities are web communication, email, DNS application protocols, and a lot more. Now, any app on your device that uses the internet interacts directly with this particular layer. Bringing it all together, a simple way to understand the relationship between two models is OSI is detailed and structured, great for learning and troubleshooting. TCP/IP is practical, the real-world implementation we use daily. You can refer to the table which is on my screen. So the OSI model and the TCP/IP model both describe how data travels across the networks, but they group functions differently. At the top, the application layer of the OSI corresponds directly to the application layer in the TCP/IP. The presentation and session layers in the OSI are also the part of TCP/IP's application layer, handling tasks like data formatting, encryption, and session management. The transport layer in both models handle reliability, data delivery, error checking, and flow control, ensuring end-to-end communication. The network layer in OSI maps the internet layer in TCP/IP, responsible for addressing and routing data between devices across the networks. Finally, the data link and physical layers of OSI are combined into link layer in TCP/IP. This layer manages local delivery of data and the physical transmission over the hardware. Together, these models give us a complete picture of how data travels from signals on a cable to the web page that appears on your screen. Now, let's go to our next module. So the 11th module is about key protocols. It explains how devices speak the same language. Networks are only as good as the rules they follow. These rules are called protocols, defining methods that ensure devices can communicate accurately, efficiently, and securely. Without protocols, your devices would be like strangers speaking different languages. In this module, we'll explore some of the most important networking protocols you interact with every day. The first one, HTTP or HTTPS, the web's communication standard. When you type a website's address in your local browser, you're using HTTP, which stands for Hypertext Transfer Protocol. HTTP allows your browser to request web pages from the servers. Now, HTTP with an S is the secured version, which encrypts the communication, protecting sensitive data like passwords, banking info, and personal details. Now, why HTTPS matters? It prevents attackers from eavesdropping or modifying the data between you and the website. Think of it like sending letters in a sealed envelope rather than a postcard. Now, the next one is SMTP. Sending emails. SMTP or Simple Mail Transfer Protocol handles sending emails, ensures emails leave your device and reach the recipient's mail server. It works alongside the other protocols for full email functionality. SMTP is strictly for sending and not receiving messages. The third one is POP3 or IMAP, receiving emails. To get your emails, devices use either POP3 or IMAP. POP3 stands for Post Office Protocol version 3. Downloads emails from the server to your device. Once downloaded, they may be removed from the server. That's a different thing. And it's best for single device email access. IMAP or IMAP stands for Internet Message Access Protocol. This keeps emails on the server and synchronizes across multiple devices. This is perfect for using phones, tablets, and laptops together. IMAP ensures your mailbox looks the same no matter where you access it. Now, the next one is TCP for reliable transport. TCP or Transmission Control Protocol is a connection-oriented protocol. It establishes a connection before sending the data, guarantees order, integrity, and completeness of the transmitted information. And the best part is it can retransmit lost packets automatically. Let's go through some of the use cases. Use cases like bank transactions, file downloads can be the best example. Applications requiring accurate, reliable communications is also one of the use cases. TCP is like a courier service that tracks every package and ensures nothing gets lost. Followed by that, we have the UDP for fast and lightweight. UDP or User Datagram Protocol is connectionless. It sends data without establishing a connection. No guarantee of delivery, order, or error correction. And let's also go through some use cases where this particular model is used. So online gaming, video streaming, voice over IP or VoIP calls. UDP prioritizes speed over reliability, making it ideal for real-time applications where minor data loss is acceptable. Next, we have DNS, Domain Name System. The internet is based on numbers, which are the IP addresses, but humans prefer names. That's where the DNS comes into the picture. It converts domain names like example.com into IP addresses that computers can understand. It uses an hierarchical structure, group to servers, TLD servers to domain servers. DNS also uses caching to speed up future requests, so your device doesn't repeatedly ask for the same question. Now let's go through a quick analogy. If IP addresses are street coordinates, DNS is the phone book that matches names to numbers. DNS is the phone book that matches names to numbers. Bringing up together, these protocols form the backbone of modern internet. Take a look at the table on my screen. So HTTP and HTTPS are protocols used for accessing websites, while HTTP handles standard web traffic. HTTPS adds security, ensuring safe and encrypted web browsing. Used in tasks like online banking, software downloads, and database transactions, it retransmits lost packets, verifies delivery, and guarantees correct sequencing. Think of TCP as a tracked courier service that makes sure every package reaches its destination safely. Up next, we have UDP efficiency, optimizing speed. UDP, by contrast, prioritizes speed over reliability. It's ideal for real-time applications like video calls, gaming, and streaming. No checks for data delivery or order, which reduces latency. It's perfect where a few lost packets are acceptable, but speed is critical. Think of UDP as a fast express lane. Some data may be dropped, but the overall flow is much quicker. Modern networks rely on these safeguards and optimizations to ensure users get a fast, reliable, and safe experience. And that wraps up our theory part of complete networking tutorial, from basics of connections and topologies to addressing protocols and finally the security and efficiency concepts. Understanding these principles give you the knowledge to analyze, troubleshoot, and optimize networks, skills that are essential in IT, cloud computing, and modern digital infrastructure. Now, let's move to a quick demonstration session where we will execute some of the basic commands for networking. So now we are on the demonstration part. So you can see on my screen we have a command prompt opened. So it's simply just go to Windows R and type CND and you'll have the command prompt executed on the screen. So right now we will execute some of the basic and essential network commands on your local system. So networking is the backbone of communication between devices. Today we will be exploring some of the fundamental network commands that will help you understand and troubleshoot any network related issues. So, firstly, you can go with color. Hmm. So, this is basically used to change your prompt color if you want. So, you can also choose any other color. So, let me go with help color. So, this will show you all the available options: blue, black, green, aqua, purple, etc. So, but the default one, let's go with the default one. I'll go with F. Now, let's clear the screen, CLS. Now, the first command that we will be exploring is ipconfig, which is a Windows command used to display the IP address, subnet mask, and default gateway of your device. This command is the first step in understanding your device's network configuration. For example, if we type ipconfig, the command prompt, we can see the IPv4 address assigned to our device. This helps you identify the network we are connected to. So let's hit enter. So you have the IP address details here, subnet mask, and the IPv4 address that you're connected to. Similarly, you also have the default gateway. So remember the gateways we discussed in the tutorial. So the subnet mask, IPv4 address, and default gateway. Now, the next one we will be exploring is ipconfig all. This particular command provides detailed information about all network adapters on your device, including hidden details like MAC address, DHCP status, and DNS servers. So, the command is simple, the same ipconfig. All you need to add is / and you need to add all and hit enter. Now, you have the physical address, and you also have the MAC address. So here you have the subnet mask IPv4 and all the other details, the host name, primary suffix, and everything else. There you go. You have the IPv6, the physical address. And then we have another command followed by this, which is called NSLookup tool. So this is a tool for querying the DNS to find the IP address of a domain name or verify a DNS resolution. For example, if you want to check the IP address of Simplilearn's website, we can type the following command. So we will type NSLookup along with website address, which is www.simplilearn.com. So this is the address. And what you can also do is you can try to try to test the connectivity between your device and the website. So you can use the same command, but instead of NSLookup, what you can write down is ping. So it sends a ping. So you can see there is a reply from the website. So we have sent 4 packets and 4 successful packets were received as well, and no data loss so far. So apart from that, we have another fundamental command, which is traceRT, which stands for trace route. So what it does is it basically helps you track the path that a packet takes from your device to a destination server. Each hop represents a network device or router the packet passes through. So let's trace the same website which we executed previously. So it is simplylearn.com. Instead of ping, what you need to write down is trace RT and hit enter. So this command helps you identify where delays or connectivity issues occur along the path to the destination. So here you can see the hops. So we had over a maximum of 30 hops. We are in currently we're at the 5th hop. So basically, to summarize, the ipconfig and ipconfig all show you the device's network configuration. NSLookup checks DNS resolution, ping tests the connectivity and measures latency, and traceRT shows the route packets take to reach a destination. These commands are essential tools for any network troubleshooting and analysis task. And this particular task will continue for at least 30 hops. So what you can do is you can quickly press Ctrl C to exit. And there you go. And we will clear screen. And with that, we have come to an end of this session on networking tutorial for beginners. And with that, we have reached to the end of this session on computer networking tutorial for beginners. If you have any queries regarding any of the topics covered in this session, or if you require any resources that I used in this session, then please feel free to let us know in the comment section below, and our team of experts will be happy to assist you at the earliest. Until next time, thank you for watching and stay tuned for more from Simplilearn.